So if we have a circuit where we have some sort of coil, sorry for the background noise. So we have a coil. This resistor here represents any resistance in the coil as well as any resistor in the circuit itself. As we close the switch to connect this circuit, we know normally if we just had a battery with a resistor, we know the current that would flow through the circuit, I, depends upon that battery voltage and the overall resistance in the circuit itself. But here, if we have a coil in the circuit in addition to this resistance, we end up getting Faraday's law applying, where as current starts to flow, this inductor originally had no current, so it did not have a magnetic field. So it initially had no magnetic flux. But we know Faraday's law tells us that if the magnetic flux through a conducting loop changes, then we get what's called an induced voltage, or EMF. That is what is going to happen when we have this coil here. The coil itself is going to resist the change in flux. So it creates, in this case, what is called a back EMF. It creates its own EMF to try to stop the flux from increasing. So this current that the battery is pushing through the circuit, or attempting to, the inductor is opposing. And that all boils down to Faraday's law because of the changing magnetic flux. So since this coil is inducing a voltage or EMF in itself, we call this self-inductance. And we call this little coil an inductor. So an inductor is a circuit element similar to, in terms of being able to put in a circuit, similar to a resistor, a capacitor. We now are going to also talk about an inductor. So just as a reminder, a resistor, the resistance itself was determined by the resistivity of the material, how long the resistor was, the cross-sectional area of the resistor. A resistor had a potential difference across it if it had current flowing through it. A capacitor, its capacitance was determined by how it was constructed. So the electrodes, if it was, say, a parallel plate capacitor, the plates, the cross-sectional area of the plates, the distance between the plates, any material or dielectric that was in between the plates. A capacitor had a potential difference across it if there was charge that had accumulated on the plates. Now, resistors converted electrical energy to other forms. So we talked about power when it came to a resistor. And that power was directly related to the brightness of like a light bulb, or how much heat or thermal energy rather was created by the resistor. Capacitors stored energy. The amount of energy they stored, we could write in terms of the capacitance and potential difference. Okay, an inductor. To represent inductance, and specifically meaning this self-inductance, where the coil will create and have an induced voltage to oppose the current flowing through it, we use a capital L to represent this inductance. The inductance, the equation for inductance is a little deceptive. For one coil or loop of wire, this inductance would be the flux, the magnetic flux specifically that will flow through the wire, divided by current. Now, in the picture I've drawn, our little coil has multiple loops, and we can account for those with the capital N, meaning the number of turns. This equation's a little deceptive, though, because inductance ultimately doesn't actually depend on the current. To see that, let's talk about a solenoid. Remember, a solenoid was wire wrapped around many, many times. The magnetic field of a solenoid was equal to mu naught times the lowercase n represented the turn density, and then the current. So those are the terms that determine the magnetic field in the center of a solenoid. Well, if we want to talk about this solenoid as an inductor and talk about its inductance, the flux in the center of the solenoid would be the magnetic field that it is creating times its cross-sectional area. But if we substitute in this magnetic field that it's creating, dog sitting, so I have extra noisy background. I apologize for that. So if I plug in for the solenoid, the flux within the solenoid itself will be the magnetic field that its own magnetic field times its cross-sectional area. But we know the magnetic field in the center of the solenoid is mu naught and I. So when we plug this fully into the inductance equation, the currents actually end up canceling out. So the overall inductance of our solenoid ends up depending upon the number of turns. Lowercase n was the turn density, so turns per length, and then A here is the cross-sectional area. So if we could look at the solenoid from the side and see the core that it is wrapped around, that's the area that we would be wanting. So this inductance is totally dependent on how the inductor is made. So that is similar to what we learned with resistors and capacitors as well. The resistance of a resistor depended upon the material it was made with as well as its geometry. The capacitance, I should say, of a capacitor was dependent upon the geometry of the capacitor and whatever material might be between the plates. So inductance is similar in that regard. Even though this equation for inductance up front, looking at it, depends upon current, the current will always cancel with the current in the magnetic field term. So this equation down here is specific for a solenoid. Any type of inductor, though, its inductance will depend on its geometry, its physical construct. Excuse me. Now the voltage drop across an inductor. Since we're talking about Faraday's law here, and we're talking about an induced voltage because of a changing flux, the inductor has a voltage drop across it. If we write it in terms of its inductance, this potential difference or voltage difference is equal to negative L, the inductance, di dt. d dt, this d dt is the rate the current in the circuit overall is changing. So the inductor, its voltage difference, its EMF based off of inductance specifically, is due solely to that change in current. If the current in the circuit is flowing and it's constant, then there's no voltage drop in terms of the inductance. Inductors store energy. So writing that over near our inductance and voltage drop equations, the amount of energy stored in an inductor depends upon its inductance as well as how much current is flowing through it. So at the moment in time, if we know how much current is flowing, we can calculate how much energy is stored. So coming back to our circuit, actually, I need to mention the units of inductance. Units of inductance, well, flux is a Tesla meter squared, B times A. Current is an ampere, so amps. We call this a Henry, the name Henry. We use a capital H to represent that. So if you buy an inductor, it's going to be some number of Henrys will be its inductance. So if we look at a circuit that's similar to what I started with, we have a battery, we connect it, well, let's start with this, with a switch. So we start with it open. We have a coil of some sort, which is our inductor. And then R, this resistance, will represent any resistance in the circuit. So it can account for any resistance of the wire itself, as well as the coil itself, as well as any inductor that we have. So before the switch is closed, there is no current in the circuit. That means there is no magnetic flux. That's supposed to be a C. Magnetic flux in the solenoid or the inductor, in that coil over there. So if there's no current flowing through it, it is not producing a magnetic field. So if there's no magnetic field inside of it, then there's no magnetic flux at all. Okay, let's close the switch. We're going to call this time equals 0. As soon as we close the switch, we have a complete path for charges to move through. And so the battery starts pushing or trying to push current through the circuit. There's an electric field everywhere within this circuit, but the coil, this inductor, had no current, it had no magnetic flux, and if now it suddenly has current, it's creating its own magnetic field, which means it has magnetic flux. So because the flux changed, this inductor creates its own potential difference. it has an induced voltage that is opposing this change in current. It had zero current, and now suddenly the current is not zero anymore. Or at least the battery is trying to push current through the circuit. So the negative sign in this potential equation, this delta V for the inductor, is our Lenz's law. It's talking about the opposition to the change in flux. Now the resistor, of course, we've talked resistors already. The voltage drop across the resistor depends upon how much current is flowing through it and its resistance. So initially there was no current, so there was no voltage drop across the resistor. Ultimately, the role of the inductor is to limit how quickly the current in the circuit will reach a final maximum value. What we end up seeing, this graph represents the overall current in the circuit. The inductor initially opposes any increase, but it can't forever oppose an increase. And so what happens is the inductor causes the current in the circuit to increase gradually. Now that's not necessarily the right word. Gradually in that the current itself cannot jump instantaneously from 0 to some final value. Gradually meaning we see this slope leading up to some maximum or steady state constant value. And this value here is the value the current would have when there's only a voltage drop across the resistance in the circuit. And we'll talk about that in just a sec. So the inductor causes the current to increase gradually to its maximum final value. Let me write better. Maximum final value. Now this happens quickly. That's why it's kind of weird to use the word gradually when we're talking in our everyday language and just talk about something gradually occurring. It brings to mind something that takes a long time, which is not the case. So gradually means the inductor does not allow the current to just immediately jump to some final value, but it still increases quickly. Now, if we think of our inductor, it's always opposing a change in current. Well, the di dt portion is the slope of this graph. So initially, the slope is steep. The slope is steepest right when we close the switch. As time goes on, this slope gets shallower and shallower until eventually the slope is 0. That means the delta V for the inductor, there is no potential difference due to inductance anymore. So if we come back and look at our circuit, if there's no potential difference across the inductor anymore, then the entire potential difference is across the resistor. So as time goes on, delta V for the inductor decreases. The rate at which the current is changing gets smaller and smaller and smaller. But delta V for the resistor increases. And that's because Kirchhoff's loop rule still must apply. If we go around this loop, battery minus the inductor minus the resistor, those have to add up to be 0. So delta V decreases, it gets smaller and smaller and smaller, eventually it is 0. The resistor's voltage gets bigger and bigger and bigger, and it eventually reaches the battery voltage. So if we come back over to our graph, this maximum current occurs when the battery voltage is entirely across the resistor. And so this maximum current depends upon the battery voltage divided by the resistance. We end up with an equation that describes the current flowing in this circuit as a function of time. Now, I don't like the subscript our author originally chose, and I'll explain why. So this is what our equation looks like, where tau is L over R, so the value of the inductor divided by the value of the resistor. This is a time constant. It's how much time it takes for the current to increase to 63% of the maximum value. I naught is not initial current. Because remember, we said before the switch is closed, there's no current in this circuit. So that wouldn't really make sense to put in 0 right there, because if that's 0 right here in our current equation, then there's no point of having anything in the parentheses. I naught represents the maximum current instead. The peak, the biggest, that steady state, constant value that the circuit will eventually reach. So that I naught is the battery voltage divided by the resistance. We call this circuit, you'll see it named this way on the test notes, a charging LR circuit. This is still considered a DC circuit. I don't know that I've mentioned that before. DC means direct current. It means there's a constant potential difference supplied to the circuit. Charging is a little bit confusing in that the inductor itself is not becoming charged in that it has more protons or electrons. It's charging in that the energy it stores is getting bigger as the current flowing through the circuit gets bigger. So this energy is directly related to the current. So if we increase the amount of current, that in turn increases how much energy is stored. So that's really what we mean by the charging situation here. So in terms of a charging circuit with an inductor and a resistor, the current through the circuit increases as a function of time. The inductor overall just does not allow the current to instantaneously jump from 0 to some final value. The inductor controls how fast that current changes. Now, as soon as the current does reach, so if we're over here in our circuit and this current has reached a maximum, there's a nice big magnetic field in the inductor. And that is where and how the energy is stored. So if we happen to have an inductor that has been connected to a battery, but is disconnected from the battery, so some sort of current has been flowing, and it was flowing both through the inductor and the resistor. This inductor is storing energy in its magnetic field. When the battery is disconnected, taken off, and if we have a path for the current to flow through, the inductor again is going to oppose the change in current. Well, with the battery gone, the current's going to go to zero because there's nothing to keep the charges moving. This inductor is going to oppose the disappearance of the battery. So the inductor, if I come over to the coil over here representing our inductor, the inductor is going to act as if it were a battery for a short period of time. It can't do this forever, but it's going to use the energy it has to try to keep this current flowing. So ultimately, the current in the circuit overall, instead of just instantaneously going from some initial value to zero, it cannot drop instantaneously to zero. The inductor causes the current to gradually go to zero. So the inductor causes the current to decrease, in this case, gradually to zero. And again, gradually this is still something that's happening very quickly. The thing we want to remember is that the current is not at that exact instant. It cannot instantaneously drop to zero. So we get an equation that describes the current in the circuit as a function of time. In this case, this is the initial current because we are starting with some value of current flowing through the inductor. It's determined by what the inductor was originally connected to. The tau is the time constant, which is L over R again. So the value of the inductor divided by the value of the resistor. So if a battery is removed and we have a path for those charges to move through, we will have this situation, which we call a discharging LR circuit. It's not technically losing charge. It is that the energy is decreasing. So the inductor uses the energy it has to try to keep the current flowing. And the net result is just getting the current in the circuit to more gradually drop to zero. So these circuits are called LR, and technically we could see them as an RL, the L meaning inductor, the R meaning resistor. So that's what we mean by an LR circuit. So I'll do a couple examples and show how to use these equations. Keep in mind, though, that the resistor, the voltage drop across the resistor is still IR. It's still Ohm's law that we used before. So we do need to draw on previous equations for the resistors. Kirchhoff's loop rule still applies. So keep those things in mind as you look at problems.